Okay, so I hope everybody can see my screen. Let me just double check to see whether I can check the chat. Hi. Okay. All right. Can you guys hear me?
Hi. Yeah.
Yes. So I have two co-hosts. I have Anand and Yashwant. That's good. So everybody else, I guess you're on the stream, right?
Yes.
You can just drop a hi on the chat just so that we know you're all here and I can get started. Hopefully, again, I can keep this session short. But this is a very interesting session that we're going to talk about. Obviously, we're not going to be able to, dive deep because atomics is a topic that, you have to get an intuition for it. You have to spend some time with it to understand things like the memory model and memory ordering, etc., which we will go through. At least you'll get a very, a good sort of well-rounded overview. At least a very high-level overview is something that I'm aiming to achieve, right? So, by the way, everybody can see my screen. You should be able to see, the actual Melon app, I hope.
Yes.
Yeah. Okay. So let me get started. The first thing I want to talk about was I actually wanted to jump directly into, what atomics are. So basically, what atomics are, if you actually go to Rust's documentation, like for example, if I was to look at this, you will see, where is that? Sorry. Yeah. No, I don't want the Nomicon. I just want the standard Rust documentation for atomics. Okay, first things first, the font size is good, right?
Yeah.
Right, cool. So think about this. What atomics are, so far when you've been writing code in Rust, or for that matter in any language, you've been writing code using non-atomics, in the sense whenever your code, like when you compile your code and you actually look at the assembly instructions, you will see that it's possible that when you're actually attempting to, for example, do something like this, you're basically trying to say that if there is, how do I give you a good example? Let's say that you're trying to say that if there is a Boolean value that you have somehow you've stored in some variable, you want to check whether that variable, that Boolean value, is, say, false. If it's false, you want to say that, I want to set that to true. What would you do? You would normally have to read it first, then check to see whether or not it's false. If it's false, then you want to set it to true, correct? Now, given that is the case, if you want to do something like that, you actually do a read and then a write, right? So keep this in your mind, that most of the instructions or operations that you sort of write in the form of code, which gets compiled down to binary code, you see that they are not atomic. The first thing that needs to come into your mind when somebody says atomic, it means that this is an indivisible indivisible operation, in the sense it is an operation that either completes or does not complete. There are no, it's, for example, if I ask you to add a number, it's not like I added 4 bits of the value, then the remaining 4 bits, for example, I wanted you to add 2 U8s, in other words 2 bytes 2 byte values, which are integers. I wanted you to add them, and you said you issued an instruction to the CPU. An intermediate state would mean that the processor was able to, like, just take an example. It was able to add the first 4 bits of the U8 and not the last 4 bits, and then you probably got a value. That is an intermediate state. In an atomic operation, that's not possible. I'm just giving you an example so that you understand that atomic operations are indivisible, in the sense they are not, you can never see an atomic operation in some, in some, you can call it an undefined state, right? Because if half of the operation happened, but the other half did not, it means it's undefined. You will never see that happen. And that's where atomics come into the picture, and that's where it's useful. Immediately when you think of this, that means atomics are only useful when you have multi-threaded code. That means you have multiple threads, right? If you have a single threaded app or whatever, it doesn't really make sense, because technically speaking, the dependencies are usually going to be maintained in there. When you actually execute a sequential program that's single threaded, atomicity doesn't really matter. Okay, that's the first point I want you to keep in mind. It's atomic types, as you see over here. Atomic types provide primitive shared memory communication between threads. And
Yeah.
by the way, this is the building block for pretty much all concurrency that you have in systems programming. When you, for example, want to build, which we're going to do right now, is because many examples on the internet actually talk about mutexes, and mutexes are actually built on top of atomics. You'll see what I mean when I talk about a concrete example. And Rust atomics follow the same rules as C++ or other C++20. So basically, creating a shared reference to one of the Rust atomic types corresponds to creating an atomic reference in C++. We're not bothered about C++ as much, but just know that it sort of follows the same rules. Whatever atomics we are using. So if you happen to read something that's written for C++, you could probably apply it, but you'll sort of have to take care of all the Rust specific differences. In Rust, what you have is you have these primitive types which are atomic. You have an atomic bool, you have an I size and a U size, you have a I8 and a U8 and a U16 and all of that. You have all the primitive ones that you need. Then you also have this thing called the ordering, which we will talk about quite a bit. And then atomic variables. The other important thing is they are safe to share between threads. That means they implement the sync marker trait. Okay, so there are 2 traits which we'll also be implementing. They are marker traits. There's no implementation for them. We just mark them, saying that, okay, if I mark a type with this trait, if this whatever X type implements the sync trait or X type implements the send trait, the sync trait basically means that you can share that value between threads. You can pass ownership around. The send trait means you can pass ownership around. Sync means you can share that value between multiple threads. That means multiple threads can have access to that value. In other words, that memory location. Okay?
Yeah.
The other thing is, the most common way to share an atomic variable is to put it inside an arc. And the reason, if you actually think about it, what is an arc? An arc is an atomically reference counted pointer. All right? In other words, it is nothing but it's built on top of atomics again. That is why it's arc. It's actually got an atomically incrementing counter, which I will simply implement for you directly now and show you. So far, so good. Just, to take a pause and sort of look at the questions. Yeah. So far, any questions? At least, like, I know that's not news. You probably already know what atomics are, right? Okay, so let's take a look let's actually write some code right now. I'm going to actually start from scratch. I have a longer example just so that we don't waste time. But for the simpler example, I'm just going to create a crate from scratch and just go with it. So let's see cargo new basic atomic. I'm just going to call it basic atomics. Okay, simpler.
Mm-hmm. Yeah.
So I just created that. I'm just going to say basic, and let me jump into it. All right. So we're here. Okay, fine. Now there's not much. I'm just going to sort of delete this. Okay. So first things first, I'm just going to say, let's say I have a counter. Let's say I have a counter that is an atomic type. I call this an atomic. I call it an atomic U32 or U64. Big deal. Okay, I'll call it an atomic U64, and I will just say, I'll go ahead and I'll walk you through what all this means. But atomic U64, and I say new. I start with a 0. So this is my counter. Obviously, I'm supposed to pull all of this in. It's going to throw errors otherwise. So all of these atomic, atomic types are sort of namespaced under atomic. So
Okay.
where did I go? Okay, anyway, it's not throwing an error, so I don't care. So we just created we basically have a counter. We're saying that this is an atomic counter. In the sense, this value is an atomic. So I want you to keep in mind like 4 things. Memory. So you can think of the system memory that's offered to you as memory locations. You can call this a memory location. Okay, there's a memory location somewhere in memory which I have made atomic. Then there are threads that I'm going to be spawning right now, which will operate on this, on these pieces of memory, or rather these values. All right, that's the second one. The third thing is the operations have something called ordering, which I mentioned. I'll talk about that a lot more. The last piece that you need to remember is each thread that I'm going to be spawning, that's going to be accessing this memory location. Each thread that's going to be accessing this memory location has its own view of what the value is over here. Okay, that's an important piece. Each thread has its own view. All right, I hope that's sort of making sense. I hope that's sort of making sense. Yeah.
Yeah.
Okay. All right. So now if I just say something like, let's just go use the Rust method and say, let threads equals 0 to, I'll just say, 10,000, something like that, and then say map them. So this is all, your Rust code you probably know and love. I'm going to say map each value to a new thread. So thread, oh, sorry. And so I want to move in this. And I want to move. All right? I don't know why my screen is like jumping off to the side, but fine. So I want to basically say, I want to take this counter and I would like to keep incrementing it from each of these. So basically, what I'm doing is I'm trying to spin up at least 10,000 threads. Okay.
Mm-hmm.
And in each of those threads, I just want to simply increment this counter. Okay.
Yeah.
Now, you can think of this particular counter as the same thing as your arc, the arc type. I mean, the implementation is probably going to look the same. I don't know. There might be a lot of details inside there talking about, how you increment the counter and all of that. But for all practical purposes, this is exactly what you're doing. You have a counter that's atomically incremented with an atomic reference counter. So every time with an atomic reference counter, what happens is you you allocate some memory on the heap, and then you get a reference back to it. Now, the moment you get a reference back to it, you can clone that reference, and then you can have another reference pointing to it, which you can pass to another thread. The way these references are incremented, that means saying how many references are there, because if the last reference goes out of scope, you can completely drop the thing and clean up memory. Okay, that's what atomically reference counting means. But the fact that you can do it across threads is why you need the atomic. Does that make sense so far? Let me just so I get this. Does that make sense so far?
Yeah.
Yeah. Okay. So let me go back and come back here. Now I'm going to go ahead here and just say, the way you actually do, counter, atomic operation, with the way you actually add stuff is you basically say a counter, because this is an atomic. Now you can do something like a fetch add, or you can do something like a load, which is, I'll show you. So if I do a load and a store, you will see that there's a problem with this. But if I do a fetch add, then you will see that there's no problem with it. So let me try the fetch add first. And I will just say 1. And then you also need an ordering. I'm just going to say ordering is relaxed. All right. Okay. Not human, relaxed. I'll talk about what this is. Okay. Just give me a minute. Yeah. Oh my God. Why is it going off to the side? Yeah. This should be easier to see, right?
Yeah. This is better.
This is better, right? Okay. So basically, that's all I'm doing. I've spun up about 10,000 threads, and I've said, you know what? All of you, each one of these threads, just add 1 to the counter.
Mm-hmm.
And after that, you need to sort of return the result. So let me just do this. So I do threads dot into iter dot okay, yeah, that into iter, and then wait. I presume you know this stuff, right? This is basically what you would call, you're joining threads so that your main thread doesn't simply exit out while your other threads are running, right? What's the issue here?
Yeah.
Expected unit type received what? Map closure. I don't think you need this. Sorry. Missing something here. Wait, I just wrote this. So let me just come back here. Sorry. Sometimes that happens. So yeah, for each, keep forgetting. So I want to take each thread and I want to do thread.join. Okay, so I want to do a thread dot join and an unwrap. And what's your problem now? Consider a semicolon. Yes, I will consider a semicolon. Take it and go. Let me just run this and see what the problem is. And it's always important to run this in release mode, okay? Because
Mm-hmm.
that
Okay.
is because atomics and the support for that, it might mess it up when you're in debug mode. At least I've not seen it, but it's sort of better to sort of just do that. Yeah, I think we've done. Oh wait, what are we doing? You expected what? For each join handle, thread dot join unwrap. Yep. Okay, so this should sort of solve it.
Yeah.
That solves it. Now let me just sort of print this out. So uh, let thread, or rather, what do I say here? This is not a thread. Let count equals counter dot load. Where is that? Hey, what's the problem now? Oh, sorry. The ordering was not specified. The ordering over here, we can just make this relaxed as well. Huh. They want me to do this. Wait. Okay. So I go ordering relaxed, ordering relaxed. So this makes sense, right? So I'm just going to go ahead and do a print
Yeah.
to see what happens here. Right. So this should technically give me what? Any ideas? Yeah. What should this give me? Any takers? Let's run it. Should it give me exactly 10,000? Right? Because what did I say? We've got 10,000 threads. Each thread is going to be incrementing this single counter. All right. And all of this is happening concurrently because any
Mm-hmm.
thread can be running at any point in time. Correct? When that is happening, you want to ensure that you don't end up, um, you know, like when one thread is sort of writing, another thread is not overwriting what the other thread has done. Like if thread one has written one, like has incremented the counter value by one, thread two shouldn't just come and say, okay, it was zero. Now again, I have incremented it to one, which means you lost out your count, right? It's supposed to be two, but you lost, one, right? And that can easily happen when you're
Yeah.
talking
Okay.
about multi-threaded code, specifically when multiple threads are acting on a shared memory location. And that is exactly where atomics come into the picture. right?
Mm. Correct.
So
Yeah.
I could do this in a different way. For example, I can also do this like this. I can do a load, which means I don't need to do this. I can do a load, and then I can do something like this. Counter load. Wait. I can do a load. Then I can do. I can take the counter and I say, oh wait, let's actually do this. Let count equals this. Okay, I'm just going to do a load. Then I'm going to say, um, I want to increment the counter by 1. In order to do that, I'm going to do a counter store now. The way I do the counter store is I simply say store. I need to provide the value. In this case, I'm going to provide the value. Or the other way to do this is I'm going to increment the counter, which is this has to be mute. So I can do count plus equals 1, and then I can do the store, which means this will be count, and this will be the ordering. Again, this is also relaxed. I'll get to this part. Now, when I do this, what do you think the value is going to be? Any guesses? Any guesses for the guys on the stream?
It would be same, I guess, about 10,000 because we are adding one to it.
Well, technically, right. All you're doing over here is you basically load the value, read the value in, you increment it by 1, and you store. Like
Hmm.
basically, you've incremented it once and you stored it. Correct. Yeah. Anyone
Yeah.
else on the stream wants to give it a shot? Any answers from the stream? From the guys online. Sorry. 20,000. Yes. Rust Planet wants to really give it a shot. Okay. Let's see what happens. Let's actually go run this. Let's keep running this for a bit. We keep getting 10,000. Now that's okay, but let me just try and increase that. So now I'm moving from 10,000 threads all the way to 100,000 threads, right? So this is 100,000 threads, right? Make sense? So you did get your
Yeah.
10,000.
Okay.
Now I've just moved it up to 100,000. What do you think is going to happen? Questions? Sorry, options? Guesses? Well, technically it should be the same, right? It should
Well,
be
now it would
100,000.
be 100,000.
Yeah, technically it should be 100,000, correct? Because that's what we're expecting. Our intent is, I just want you to increment the counter. I'm going to spin up
Yeah.
100,000 threads, and each one of them is going to increment the counter by 1, right? So ideally speaking, you're right. It should be
Yeah.
100,000.
Correct.
Let's see what happens. Damn, my computer's fast. So the this particular thing didn't work, but technically it should have worked. I don't know if maybe if I include but that's a little bit of a cheating. But okay, if I include another 0 here, I don't know what's going to happen, but let me just try. I'll include 1,000,000 threads. Okay, let's spin up 1,000,000 threads. Hopefully my computer doesn't die. If it dies, I'm not the one responsible. I'm just telling you right now. It just so happened that, you know, stuff happened. Hopefully, just don't crash, okay, please. Uh, okay, great. It's stuck.
Still stuck?
Damn.
Oh, yeah, got it.
Okay, but that million answer, uh, I just don't know what's. I don't know if Apple Silicon is so amazing that it's getting all the calculations right. But technically, you know what happens? This is not supposed to
Mhm.
give me the same answer. And anyone wants to take a guess why? Like even if I tried this, like even if I went down to like 100,000, even if I went down to 100,000, you might have seen some issue. It's not always going to show up when you actually do it, for because computers are extremely fast, and if the scheduling is done right, etc., you may not see it. But there is some issue with this. The bug may show up in production. For now it ran, you got the answer, but that may not be the case always.
Mm-hmm.
Okay, is that making sense? And why do you think that could be the case? Why do you what do you think the bug is over here? Remember, I talked about indivisible operations. That means an operation is considered atomic when either it completes or it doesn't complete. It doesn't. There's no intermediate state. Only that operation is called an atomic operation.
Yeah.
If in this case, if you look at it, line number 9 and line number between line number 9 and line number 11, you have a load and then you do a store. So what
Mm.
happens is one thread is reading the value, which means it's loading the value. The other one is writing to it. All right. So, but that's the same shared memory, right? It's a shared memory location, correct? The
Yeah.
counter is one global variable. It's static, correct? It's a global static variable that you have access to. All threads are
Mm-hmm.
modifying the value of counter. Now, one thread is reading, let's say, 0. While it's reading 0, the other thread goes ahead and increments the value. Okay.
Mm-hmm.
So one of the threads did not read, in that sequence, one of the threads did not read the right current state of counter, right? Because there's a difference when you actually separate the instructions out, the load and the store, they're not happening together. If they happen together, then no thread can squeeze in between and say, okay, I read the value, I'm going to increment it. The other guy will come in and override the same value with the same value. That means two threads may have written, may have incremented from 0 to 1, rather than one thread doing it from 0 to 1, the other thread doing it from 1 to 2. Yes.
But isn't it is possible because we are using atomics?
Yeah, the operation, that means that's a very good question. The operation,
Mm.
this operation is atomic. The load will fully load your value. It won't load it half and it won't load it, the other half will come in later. No, the
Hmm.
operation is fully atomic. The store that
Yeah.
you write, you're not writing half, a bunch of bits here and then a bunch of bits to count. You're writing all 64 bits, right? When
Mm.
you're writing those 64 bits, nothing else has access to that. That's the other thing. When you're reading the value in, you're not, you don't, no other thread sort of has read access to it, or they have read access, but no other thread is actually giving you, um, coming in between that during that load operation.
Mm-hmm.
Okay, but between the load operation and the store operation, there's some time, right? Of course, this is nanoseconds, but there's time. my thread could have, the other threads could have come in by then, right?
Yeah. That particular thing is not. We are not sure about that.
Yeah. So
Yeah.
technically, I should have seen a different value over here when I
Mm-hmm.
saw this. So that is not happening here. I presume sometimes computers are too damn fast and too damn good for their own good, because you can't
Yeah.
find bugs with them. It's possible. So that's one of the cases. And this is exactly what I wanted to
Mm-hmm.
demonstrate when we talk about atomics. The fact that operations that are
Okay.
indivisible are important, because when we actually do it, you want to read the value and then you want to write to it. You don't want the read to happen first and then wait a little bit and then do the write. If you wait a little bit,
Mm-hmm.
you're not actually waiting, but if there
Mm-hmm.
is some amount of time between the reads and the writes, anything can happen in between that time. The reads may be atomic,
Yeah.
the writes may be atomic. But while reading and while writing may be atomic, but the period of time between them is not.
Mm-hmm.
Okay. Now that we are already
Yeah.
here, I'll also talk about ordering. Ordering has to do with the way instructions are, or in other words, this is called memory ordering. In the sense, when I say it's relaxed, all I want you to guarantee is that the operation is atomic. I don't care about whether the compiler is going to reorder some of these instructions, right?
Okay.
For example, when I do a load, it has no dependency on any other instruction. It can actually be reordered, right? You can move one, the compiler can do it. This is all stuff that you don't do it. When you compile, either for performance sake or for optimization, for whatever reasons, depending on how the compiler generates code, binary code or assembly code,
Mm-hmm.
it is allowed to go ahead and reorder these instructions for whatever reasons. Okay, the compiler can do it, and the memory model allows it according to the spec, is what you'll keep thinking. That is what relaxed means, because we don't really care where these operations are, is what we're saying. Okay, making sense? Does that make sense?
Yeah. Yes.
So ordering is primarily focused on the fact that you're looking at whether or not when this operation happens, operations before it and operations after it, what is the effect on them? That's what you want to keep in mind when you use an atomic. Okay. The next atomic ordering that we'll be talking about is called acquire and release. There are actually 5 of them. So let me just quickly
Mm-hmm.
pull up my notes. So yeah, here's the thing about atomics. I just made a couple of notes. Atomic operations are indivisible. That means they are always what you'd call, um, you know, they either complete or they don't. There's no intermediate states and all over there. There are 3 different types. One is the load and the store, which is read and write, and then there's the read, modify, write, which is sort of happens in one go. We haven't talked about the read, modify, write, but fine. Um, the other thing that you need to keep in mind is atomics are not actually, when I keep saying atomics, right, it does not mean that uh, this is just the compilers doing all of this code generation, etc. Hardware must have support for this. Atomics are not available, for example, on those low end microcontrollers that we have. Some of them don't have atomics. The CPU does not have support for atomic instructions. All right. The assumption is all operations are non-atomic on those CPUs. So hardware must have support for atomic instructions. All right. That's the other one. Then atomic operations are guaranteed to execute as a single instructions, which is what I just mentioned. This other piece that we talk about, which is something that you must have now figured out with this example. With this example, you've figured out that they limit what the CPU can do and what the compiler can do about a given memory access. Because once you mark some variable as atomic, then when the compiler compiles code and when the CPU runs that code, they are limited in what they will be doing about it. Because when the compiler compiles code, it's going to generate a specific set of instructions. Okay, they are atomic instructions. Atomic instructions are the actual instruction changes. It's like CAS will be the, the mnemonic for in assembly, etc. All right. I did not have the time to put together the assembly instructions, but just know that the instructions themselves are different. Okay. Any questions on that? Checking. Nope.
No.
No questions. All right.
Yeah.
Cool. So we can move forward. And I already mentioned the gist. So we went through the what sort of atomic values can we have. All atomics are usually primitives. They are not like your custom data structures and all. They're not. They're primitives, like your booleans, your integers, your I sizes, your U sizes, all of that stuff. And we also talked about load, store, read, write, etc. We talked about memory ordering. Like they are like barriers, is what I mentioned, right? So if I have this atomic operation here, generally ordering will this ordering input, the ordering that you provide will determine whether or not instructions before it or after it have some bearing. You need to like worry about those things. That's what ordering is about. Anyway, this will become a little more clearer when we talk about acquire release. We'll get to that point. And a little more detail about memory ordering. The order in which a particular memory location or an address is accessed is what memory ordering deals with. Again, I'll show you more details about that. Okay, this is sequentially consistent. These are all rough notes, so just take it for what you will. But there are 5 types of memory ordering. There is relaxed, which you just saw, where I've told you that there are no guarantees, in the sense you can see any value written by any thread to the memory location. Like in this case, counter is the memory location that we're worried about. Any value written by any thread can be seen. There are no restrictions whatsoever. That means while the atomic operations are atomic, okay, there's no intermediate reads or intermediate writes states. That is atomic. But there are no guarantees on the order of accesses. Matlab, when did one thread actually come in, and when did the other thread actually let go of that memory location? None of that is available. There's no guarantee on that. It can happen however it wants. That's why it's relaxed. Okay.
Okay.
Then acquire and release. This is the 2 that we'll be talking about. Sequentially consistent and accrel are all sort of built on top of this. So acquire, release are the 2 ones that I will cover. And that's how we'll also build a mutex as well. You'll see right now. So just keep this in mind. Any instruction prior to an instruction with this ordering cannot be reordered or moved to after it. I'm oversimplifying things, but oversimplification is good to start with. When you get into it, you can know the very, very nuanced language that is used. Because if you actually read the language, that means if you go to, I don't know, here, if you go to the actual C++ standard and read it, there's quite a bit of all the memory orderings are listed here. You can see a whole bunch of things. Without diving into this, I'm just trying to make it a little more simple. If you see here, for example, if let me actually jump in here because I knew I would not have time, so I already wrote it. Okay. So this is like a simple implementation of a mutex. Let's look at it this way.
Okay.
I first declare my mutex. My mutex is nothing. A mutex is nothing but an unsafe cell. It is a cell that holds some t, and then it has a lock on it. This variable or this field is called the lock field. So what does the mutex do? You take a lock, you lock it, then you do whatever you want with the inner value, and then you release the lock, right? That's what you do. While I have the lock, nobody else has access to the inner value, which is t in this case, right? Very simple definition of mutex, or like very simple description of mutex, right?
Yeah.
A mutually exclusive type, whatever. So what I do is I first have my, I'm first defining my type, and then a simple implementation. Create. How do you create a mutex? I simply go ahead and give you the value, and then I'll create the mutex. That's fine. Now the important thing is this lock function over here. We will get to that, but before I get to that, see what lock returns. It's called a mutex guard. Now mutex guards are something that it's not new. Okay, this is something that we've, if you go into the Rust documentation, you'll find a lot of this explanation over there, right? What I've done is a very, very simple implementation. So this is actually part of what is called RAII. Anybody remembers what RAII is? Resource acquisition is initialization. It's been a long time, but we went through that. Anyway, so let's look at it this way. A mutex guard is something that whenever you lock the mutex, instead of you getting whatever you want to get something back, right? When you lock it, you want some way to access the value, that the mutex is protecting, correct? Instead of giving you that value back, you just give a mutex guard which holds the value. Okay.
Yeah.
That's what I've done here. If you see here, a mutex guard is nothing but it's a reference to a mutex. Like think of it as a wrapper around mutex. Okay. Make sense?
Yeah.
I just wanted to call that out. I hope you guys remember these guards are sort of why do you have this additional type? Why can't we just use mutex? We discussed that a long time. Anyway, that's not important right now, but just know that we're using the mutex guard. If you sort of go back to the previous streams, you may find it. So when you lock, I get my mutex guard back. Mutex guard is nothing but, it's a wrapper around a mutex. So big deal. So here's what's happening. What we're doing over here is, what did I say? What is a mutex? So mutexes only make sense when we're talking about multi-threading environments anyway. When one thread has a lock on that mutex, it now has access to the inner value protected by the mutex, correct? So when I call lock on it, I must somehow end up having exclusive ownership, or that's the Rust term, right? Exclusive access to that value. Nobody else should be having access to it, right? Yes?
Yeah.
That's sort of what you're trying to do. So the lock implementation is doing that. So it says self.lock. Lock is what? Atomic bool. So I'm going to set, usually I start out as false, right? When I create a new mutex, I'm assuming that it's not locked. So the lock field is set to false. So now I'm going to set it to true. That's what the swap method does. The swap method is very simple. Whatever value you've given me, I'll swap it out atomically swap it out with the existing value. Okay. Does that make sense? So for example, what I'm doing over here is, let's say there's one thread that is trying to get the lock. When it says that thread says lock, you hit this line of code, and this line of code is going to say, okay, let's assume that that's the first thread. Okay, the lock is available. That means the lock, it's not been locked. The mutex has not been locked before. So that thread is going to get access. So what it's going to do is it's going to take the swap method is going to read what's inside, is going to take that, going to get that value, and then going to write true to it. And that's it. All right. And when that happens, when it returns, so if you look at this, stores a value in the Boolean and returns the previous value. In our case, the example that we took, the first thread is what? the first thread gets to see false, right? So it returns false. So while false, it just comes out of it. The loop breaks. Making sense? Yeah. So basically, the loop breaks. The next time, what happens is, let's say there's another thread. This
Yeah.
thread has the lock now. Now, when there's another thread that tries to do the same thing over here, it tries to acquire the lock, but it's already true. It'll call swap true, and then it's going to write true again back to it. So it's going to return another true. So it'll keep looping. The lock will not release. Yes.
Yeah.
So that's the implementation of this over here. And then I'll talk. This is like you need to implement this because the type that you put inside a mutex, if it's sendable and if it's syncable, sorry, then the mutex is also same thing. You can implement send and sync for mute directly like that. And these are implementations for mutex guard. Mutex guard, this is not very complex implementation. This is basically deref in the sense, if I want to get the direct value inside of the mutex guard, I'm implementing it as a method. So whenever I do the star, deref gets called. Whenever I do star mute or something, deref mute gets called. Okay. Make
Okay.
sense?
Yeah.
That's all that is. Now, the other important thing is, okay, you talk to me about, how do I, that means you talk to me about locking the mutex, but you didn't talk to me about unlocking. So for unlocking, how does it work in unlock? Whenever you drop the mutex, that means whenever the mutex goes out of scope, that's when, you should be basically releasing the lock, right?
Yes.
So I implement drop. Generally, drop is auto implemented, right? Now I implement drop for the mutex guard. So whenever the mutex guard goes out of scope, we simply release the lock so that another thread can pick in.
Okay.
Okay? Guys in the stream, this makes sense?
Yeah. Yes.
So that is pretty much the implementation of a mutex. It's like the simplest, most basic implementation. Of course, if you go look at the standard libraries mutex implementation, that is a synchronization primitive. It's got a lot more stuff in there, etc. But this is it. This is what you're looking at. All right. So mutexes are using basically atomics underneath, at least in this implementation.
Yeah.
Okay. So here's what's happening. Now that I've done all the implementation over there, I've still not talked about acquire and release. Okay. The thing about acquire and release is when I actually do that. So let's take a look at here. What's happening? Let's just jump into the implementation. I'm saying that arc new. That means create a mutex, put that mutex inside an arc. The reason I'm doing all of this is because I need to share it with multiple threads, right? That's why you need an arc, no? I need to
Yeah.
put my data, I need to be able to share it with multiple threads. So I need to go ahead and do this. So anyway, I have 10,000 threads again. I'm basically taking those 10,000 threads and I'm saying, go ahead, lock each of these threads. You can go ahead and lock. You can increment by one, and then you can drop the lock. That means release the lock, and then some other thread can sort of pick it up or whatever. Keep going like that. All right. And then finally, I want you to print the lock. Okay. It's very simple. Whatever you saw previously, it's sort of very similar. Yep. So far, so good. Makes sense, right?
Yeah.
So now what's actually happening over here is when I actually take the lock, this method is called, correct? Now, between the lock and the drop, there's only one statement, right? Yep, that sort of makes sense. So if you go back to my simple, oversimplified, uh, understanding of acquire and release memory ordering, it says any instruction prior to an instruction with this ordering cannot be reordered to after it. In the sense, any instruction with this ordering, that means over here, let's say you're using the swap, which is the atomic operation is being called. So any instruction prior to it, that means any instruction before it, any of this stuff cannot be reordered to after this.
Mm-hmm.
Okay. And release is the reverse. Any instruction following an instruction with this ordering, that means any instruction following an instruction, that means anything that comes after it cannot be reordered before it.
Yeah. Okay.
Okay. It's like you can think of, that's why I call them barriers, at least in my head. So this particular, when drop gets called, I'm actually calling drop physically. Generally, drop does not need to be called physically because this will get auto called. Okay. But anyway, we're simply calling it. So what's actually happening here is that between these two atomic operations, you are essentially saying that when I release that memory location, that means the drop function is what actually releases the memory location. The acquire ordering is what says I'm acquiring access to that, or I'm acquiring, yeah, I'm acquiring access to that location, memory location. So if you release, all of the writes or all of the changes that you have done must be visible in that acquire. Yeah, that's what it means.
Yeah.
Make sense?
Yes.
So that's the simplest thing over when we're talking about ordering and atomics and stuff. The first thing is we are talking about concurrency. Second thing is we are talking about shared access to memory by multiple threads. When we mark something as atomic, it means that there's hardware support to ensure that the atomic operations are singular operations. They are not. They cannot be further divided into smaller operations. They will complete or they will not complete as a whole. All right. And memory ordering is mostly to do with what should happen before or what should happen after. It's usually called happens before relationship. That's what atomics are about. This is like a 5,000 level, I would call a 1,000 level of high level of 1,000 feet high level overview. All right. When you start using it, you start diving into it, then you start realizing all the odd stuff that can come out of it. Yeah. Make sense?
Yeah.
So let's check the chat. Any questions? No questions? Questions, guys? Okay, I think it's fairly straightforward. Now let's just run this and see what happens. But before I do that, I need to come out and say learn. Oh, so I created a project within a project. Great. So I do the same thing, cargo run release. It works, just like you'd normally expect it. I was hoping that I would be able to show you an actual wrong result. But that, because I don't know whether the computer is too fast or some small mistake I made somewhere. But anyway, but at least I think you get the gist. If you split those operations into two different operations, then you should expect an error, right? Because
Yeah.
There could be multiple threads that are contending for the same memory location, and they could be overwriting the other's results,
Yeah.
right? So that's pretty much, if you think about it, you just saw an implementation of mutex, and that's how you normally think about it, right? So what do you think? Did this make sense? You want to use mutexes? Oh, sorry, you want to use atomics?
Yeah, it makes sense.
Well, obviously you're going to be
So
using
other
atomics.
like locking mechanisms are also based on atomics.
Yeah, if you think about it, I just showed you that arc is another one. We can actually take a look at that. For example, if you just go to, let's strike arc. Yeah, standard sync arc. If you were to jump into the source code and start looking at where arc is, like you
Mm-hmm.
further jump into it, you'll need an arc inner. Let's go find our arc inner. Okay, somewhere up. No, not here. But you must have already seen it right now. You see this? These are atomic memory orderings. Okay. Anyway, I'll show you. Let's just sort of walk through this through. Where is the inner implementation? Yeah. See this? Yeah. The arc
Atomic
types
usage.
that you
Yeah,
just saw,
correct.
it's basically atomically reference counted. The counted part means there's a counter. Okay, that counter is firstly basically there's a
Mm-hmm.
pointer which is a non-null pointer holding an arc inner type, and if you look at the arc inner type, you just dump into it, you see that it's an actual use size,
Mm-hmm.
atomic use size. You've got both strong and weak and all of that. These are all implementation level specifics. They talk about all the corner cases and all of that stuff. We're not going to get into that, but basically that's the gist of it.
Yeah, yeah.
So you can probably look at, if you go into sync, right, you will find a whole bunch of types in sync. For sync is basically synchronization. You've got arc, you've got barriers, convars, mutexes,
Mm.
once, read write locks. Now the last part that I wanted to mention here is what you just saw when I talked about atomics. You might also hear the word lock free programming. Okay. When you hear the word lock free programming, just think if they're atomics. Right? In the atomic world, you don't need
Okay.
locks. Okay. You don't need to like lock something and make everybody else wait for you to release the lock. In the atomic world, what happens is the operation either completes or doesn't complete, doesn't make you wait. The CPU's problem, that is, not the software or your implementation. Okay.
Mm-hmm.
So that's why atomic operations are always on top of primitives. That means they only apply to primitives, and they're always running at CPU speed. They're not like waiting for anything to happen. They're not spinning and waiting for something to happen. All right?
Yeah.
Make sense? By the way, this, what you just saw, this is basically a spin lock. It keeps spinning till, till the other thread releases the lock. Here we're releasing it very quickly. We're dropping the lock, but we don't know. Maybe one thread will want to hold on to it for a little while, right? Until one thread releases the lock, the other threads don't have access to to that mutex, right? That's why
Yeah.
you are using atomics to build locks, but atomics themselves, if you're not building locks, you're not building mutexes, you're building something else. Atomics provide you an option to do lock free programming. That's what it means. So mutexes are a higher level construct that programmers can use
Mm-hmm.
to make things simpler, whereas atomics are concepts that allow you to write code that is lock free, you don't have to worry about acquiring a lock or releasing a lock. You'll have to worry about memory ordering, but not the actual locking. All right?
Yeah.
Okay, so that is basically a very, very high level overview of atomics. There are also things like, which we did not cover. There's, if you go into our, C++ standard, you have relaxed, we just covered. Acquire and release, you have some idea. Consume is nobody's using, so nobody cares. Rust does not have consume, by the way. Then acquire, release, and sequentially consistent. Sequentially consistent is the one that has the most amount of guarantees. As the name suggests, it expects that all operations are consistent sequentially in different threads, whatever it might be. The consistency of sequential operations must be maintained. That's an extra step that happens, but it's built on top of acquire, release. Okay, so my suggestion is, I think this is a very good space for you to sort of read about it. There's a very good book. Where's that book? Yeah, it's by a person called Marabos. So it's freely available. You can basically read it. So for example, the book is called Rust, Atomic, and Locks. I think I found this very, very, very interesting. There's, I picked up some of the spin lock stuff from her only to sort of explain it today. All right. Yeah. And then you also remember your channels from your IPFS work and from your OCAM work, all of that. You're building channels also on top of atomics. Right? You see this? Chapter 5 in her book. That's also the case. Okay. All right. Any other questions? So that's kind of what I had for today. Yeah, hopefully I did not confuse you more than what I should have. All right. I guess there are no more questions. So let me just double check the other chat as well. Well, this is set to all. Have I? That'll show. Questions. All right. I guess not. So that's about it for this stream. Hope you found that useful and interesting. All right. We'll catch up on the next stream, which I don't know if you want like an extension of this or something else, but we'll catch up on the next stream with probably a different topic. Right. See you guys. Have a good weekend.